Hello, everyone. This is the second in a series of lectures covering Chapter 35. Today, we'll be talking about the historical attempts to measure the speed of light, to measure the speed of light, a bit of a tongue twister, as well as the ray diagrams we'll be working with for the next couple of chapters. So, now we know that the speed of light in a vacuum is around 3 times 10 to the 8 meters per second. So that's a couple million kilometers per second. Really fast. So you can imagine trying to measure something that fast isn't so easy. And Galileo Galilei tried. He set up two observers in two towers, about 10 kilometers apart, each one with a lantern. And the first person would open the shutter on their lantern first, and the other person, as soon as he saw the light from the first lantern, he'd turn his on. So, however long it took for the first observer to show off his lantern and the second observer to then see the light and open it, that'd be how much time light had to take to travel the 10 kilometers between the towers. But the results were inconclusive. After all, light travels so fast that it covers a 10-kilometer distance in a split second. So the second observer does not have the reaction time to actually, as soon as light is seen to open it, that's already too late. So let's go to 1675, where a Danish astronomer, Ole Remmer, he made observations that would actually lead to the very first successful estimate for the speed of light. So Remmer was just trying to observe the period of Io, one of Jupiter's moons. And to give you an idea, the period of revolution around Jupiter for Io was about 42 hours, or it's like 1 3/4 of a day here on Earth. So it's pretty fast considering our moon has a period of 28 days. And the way that he'd measure a period, with his eye and his telescope on one hand on a feather full of ink and a parchment, he would start measuring, counting time from when he see Io eclipse Jupiter, and then see how long it takes for another eclipse. Because right between the times of two consecutive eclipses that Io does, it has made a full lap around Jupiter. So that must then be the period of Io. Now, the thing is, though, is that the Earth and Jupiter orbit around the Sun, and the Earth orbits much, much faster than Jupiter. Its orbit's smaller. So there's points during the year that the Earth is right next to Jupiter, relatively, and later on, the Earth is orbiting on the other side of its own orbit, so it's on the other side of Jupiter as well. And Raymer noticed that there was a discrepancy in how long the time between periods was at different points in the year. So on average, he noticed that the time between periods was about 40 hours, 42 hours, as is the period of revolution of Io. But he noticed that during the year when the Earth was really close to Jupiter, he would see that eclipses were happening earlier. That like less time, it was like a little bit less than what it should take between eclipses to be seen that he was observing. And later in the year, when the Earth was on an orbit on another far away from Jupiter, the eclipses seemed to take longer. So this seemed to imply then that when the Earth is farther from Jupiter, that the first light that we see as soon as the eclipse is over, as soon as Io peeks out from behind Jupiter, that has to travel a longer distance. It has to, if you compare E2 to E1, the light from Io has to travel about Earth's kilometer more to reach the Earth. So it must be why it takes longer to see light from Io when the Earth is farther away from Jupiter. Now, you might remember Huygens from earlier, who proposed that light was a wave. So Huygens took Raymer's data and used it to estimate a lower limit for the speed of light. Basically, you can then find the offset between the time, the period measured when the Earth is next to Jupiter to when the Earth is on the other side of its orbit, opposite from Jupiter, get that offset, and that must mean the time, that offset in timing of the eclipses must be due to the fact that light has to travel the diameter of the Earth. So if you know the offset in time, and you know that that's because light is traveling the diameter of the Earth, then from that you can calculate the speed of light. Since again, you know how long it took to travel the diameter of the Earth, and you can estimate the diameter of the Earth fairly well, even for the 1600s. So the estimate here that Huygens found with Raymer's data was speed of light being 2.3 times 10 to the 8 meters per second, which, considering the tools that we're working with back in the day, it was a very, very good estimate, again, in the same magnitude as what the value actually is. And from a historical perspective, at this time, there wasn't a concise idea of what the speed of light should be. The physicists and even French philosopher Descartes argued that light had an infinite speed, but this delay in light getting across, to the Earth when it's farther away from Jupiter, this lower estimate showed that light does in fact have a finite speed. So to get a more accurate measurement of the speed of light, it would happen 200 years later, thanks to a French physicist named Armand Fizeau. He was actually a pretty cool guy, and he had a pretty cool method that allowed him to measure the speed of light on Earth without having to use a telescope or look at any other planets. So here's a simplified version of Fizeau's experiment. He sent a beam of light through a toothed wheel, and the idea is that at the starting point, light passes through this gap in the gear. Let's call this gap A. And if the wheel's not moving, then what's going to do is light is going to travel far towards this mirror here, and it's going to bounce back and come back and cross the little gap and back the way it came. So what you would have is you'd have the observer, you have some measuring device here, and in this situation then the light sets off, passes gap A, hits the mirror, bounces back. Then if you're observing over here, then you'd see the pulse of light, you see the reflected light. Now, one important thing about this setup is that understanding how fast light moves, the mirror, the reflecting surface here, is positioned really far apart. Historically, it was kilometers away from the gear and the observer. So if you can measure how long it takes for light to travel to the observer behind the wheel, then you can actually calculate the speed of light, since you manually set up the mirror some distance away from your wheel, from your detector, so you know how far away the mirror is, and if you're able to measure how long light takes to get to the detector after it hits the mirror and bounces back, then you can just calculate the speed of light with those two measurements. And to actually be able to figure out then how long it takes light to travel, you have to get the mechanism in the wheel to make the wheel spin. Now, if the wheel is not spinning slowly, light is really fast. So for a low spinning wheel, the reflected ray from the mirror will pass through gap A. But if the wheel is set to spin even faster, if it's rotating really fast, then eventually light will pass through gap A, reflect on the mirror, and once it travels back to the cog tooth, the tooth here labeled B will be in place of A, and that will block the light. So the observer would not see anything from their telescope, from their observing viewpoint. So if you increase the rotation of the wheel even higher, you can get the wheel to move fast enough that by the time that the light leaps through gap A, reaches the mirror kilometers away, and bounces back towards the observer, towards the wheel, by the time it bounces back and reaches the wheel, the gear has rotated so that the opening labeled C is now in place of A. And in doing so, it'll let the light pass through, and the observer will see the light coming from the mirror. So once you have the rotation of the wheel set fast enough that you now begin to see light that pass through gap A and bounce back through gap C, then you can actually figure out how long the light took to travel, because you manually set the rotation speed of your wheel. So once you know how fast your wheel needs to rotate so that gap C lets the reflected light pass through, you can then figure out how much time it takes for the gear to rotate so that C is in place of A. And that's equal to the amount of time that light traveled double the distance from the wheel to the mirror. So this was like a very successful experiment, and the value that Fizeau arrived at was about 3.1 times 10 to the 8. And ever since then, the further experiments would give a more precise value. But for its time, again, 1800s, it was a very, very good experiment. So the example here talks about the experiment, again, in this kind of simple form of just a gear and mirror. And you're told that the wheel, having 360 teeth, it's rotating at some moment of revolutions per second, and basically the speed is set up so that the experiment is doing what it intends to do, that the incident ray passes through gap A and the reflected ray passes through gap C. So in other words, the cog has rotated just enough that C is in place of A. And the experiment says, okay, well, the speed of light will be, we're looking at light traveling to the mirror and back, so that's a distance of 2d, and we're trying to see how much time that is. And that time is equal to the time it took for the gear to rotate gap C to the position of gap A. So then you can rewrite this formula in terms of the angular velocity of the cog and the total angular displacement of the cog, which again, the angular displacement in this case is just one tooth moving through, right? Because there's 360 teeth, and we know that enough time has passed that A, B, and C have rotated so that C is in place of A. So that's one tooth worth of a cog moving through clockwise to get C in place of A. And because there's 360 teeth, then one teeth moving is equal to 1 over 360 revolutions. So then figuring it out that the angular displacement is one tooth, which is equal to 1 over 360 revolutions, you know the angular speed of the cog, and you know how far away the mirror is because you set it up. That gives you then an estimate for the speed of light being 2.97, which is pretty close to the truth. Here's a nice video here talking about the Fizeau's experiment in a little bit more detail. Dog Physics has also done much more physics videos than this one, and is a fairly good educational source that sort of presents things without getting too complex. I recommend him. And of course, Flipping Physics. So the next section is quick. We're just introducing the ray approximation for ray optics, and ray optics is just talking about how light propagates as it moves through different mediums and hits surfaces and reflects off them, passes through them, and so on. And the assumption that we make is that, well, light is traveling in some fixed direction, it propagates in a certain direction, and then you can just draw a line. You can draw a set of rays that shows the direction of propagation. And if something happens that makes the propagation change, such as encountering a surface or the interface of another medium, then we would just point the rays in another direction to show that refraction's happening or the reflection is occurring. So rather than having to draw a bunch of wavefronts, you can just draw waves that imply the presence of wavefronts traveling through. But it's just a lot easier to understand how reflection is occurring or refraction is occurring by just using rays. So every time you see a ray, you can imagine that it's representing these wavefronts of light that are perpendicular to the rays. And here's a few examples of rays being used in place of wavefronts. So the first example is an opening that has a size, a diameter that's a lot bigger than the wavelength of the light rays. So what happens here is that you have this big light wave coming in, and then the circular opening here, which is pretty big. So what it does is it filters all the light that doesn't reach the opening, but the light that does reach the opening just passes through undisturbed. And in this second example, we have an opening, we have a hole whose diameter is about the wavelength of the light. So in this case, what will happen is that, again, light hitting the walls just kind of gets filtered out, but the rays that do make it through will fan out after they pass the opening. And lastly, if the opening is tiny, such that its diameter is actually much smaller than the wavelengths, then this opening will actually become a point source emitting spherical waves. So this almost become like a completely new source of waves, its own ripple in a pond, to say, kind of like hitting at the reset button on the wavefront, changing the shape completely from what it was, uniform wavefronts coming in left to right, now has become a ripple of sorts. Anyway, so that's all I wanted to talk for today. Next time we'll talk about reflection and then refraction. Hope to see you then.